Chapter 14, Section 3, Regularization. As we saw in the previous chapters, overfitting is one of the major concerns in supervised learning. Deep learning also can suffer from overfitting, but we can use some methods to prevent overfitting. As such methods, this chapter focuses on regularization. Some of the regularization technique can be used for traditional machine learning. First, let's recap the concept of overfitting. Overfitting is a problem where a model is optimized too closely for a particular dataset and fails to perform well for other datasets. In other words, a model fits the training data too much, and therefore it achieves high prediction performance only for the training data, and shows poor performance for other data, such as test data. That is, the model is optimized only for the training dataset, and not generalizable to unseen data. When we create a plot of the model's learning history, the plot sometimes shows curves like these. After a certain point, the loss lowers for both the training dataset and test set. But from a certain point, while the loss keeps lowering for the training set, it begins to increase for the test set. It is a typical case of overfitting. The model fits only for the training set and deviates from the validation set. Our purpose in developing a deep learning model is to make predictions for unseen data. So, an overfitted model is useless. So, we need to take measures to prevent our model falling into overfitting. Regularization is a technique we can use to avoid overfitting by preventing the model from being too complex. Specifically, regularization prevents overfitting by penalizing the complication of the model. Here, these regularization techniques will be covered: L1 and L2 regularization, dropout, and early stopping. Before going on to the world of regularization, let's answer a basic question. We have four graphs that represent the relationship between x and y. Among them, which is a case where x and y are not related? Pause the video for a while and give me your answer. Alright, what is your answer? The correct answer is this one. In this case, the slope of the straight line, beta, is 0. In other words, the regression coefficient of x is 0. It means that x is not related to y. If the straight line rises to the right, x is positively related to y. And if the straight line is downward sloping, x is negatively related to y. When we implement hypothesis testing by using regression analysis, we test the statistical significance of the relationship between the independent variable and the dependent variable. That is, we test whether the independent variable significantly relates to the dependent variable. Do you know what are we doing there? What we do there is testing whether the slope of the regression line is 0 or not. In other words, we are testing whether the regression coefficient of each independent variable is 0 or not. If the slope is not 0, that is, the regression coefficient is not 0, the independent variable is significantly related to the dependent variable. In a multiple regression analysis, the more independent variables are included in the regression equation, the more complex the regression model is. The more complex a regression model is, the more likely the model overfits the training data. Using regularization, we can reduce the complexity of the model and thus prevent overfitting. In multiple regression, the fewer independent variables significantly relate to the dependent variable, the less complex the model is. For instance, suppose only x1 is significant in this regression model. That is, x2, x3, and x4 are not significantly related to y. In this case, beta 2, beta 3, and beta 4 are 0. So, we can rewrite this regression equation in this way. In a multiple regression model, the more independent variables are not significant, the less complex the model is, and thus, the less likely the model overfits a particular dataset. Regularization prevents overfitting based on this logic. Regularization forces some of the regression coefficients to be 0 or almost 0. The coefficients of less impactful independent variables will be forced to be 0 or nearly 0. By doing so, regularization simplifies the model, and thus prevent overfitting. In the deep learning use of the term, regularization forces the weights of uninformative features to be 0 or nearly 0. The popular regularization methods used in a regression model are L1 regularization and L2 regularization. We can use them not only for deep learning models, but also for traditional regression models. Detailed mathematical explanation is beyond the scope of this course, but let me tell you that both methods regulate the model so that the weights of features do not get too large. L1 regularization is called lasso regression. Lasso shrinks the less impactful features' weights to 0, and thus removes those less impactful features. So, lasso works as a feature selection method. L2 regularization is also called ridge regression. Ridge makes less impactful features' weights smaller. So, ridge regression is often referred to as weight decay. In the next video, we will explore other regularization methods, dropout and early stopping. Thank you for watching. Please thumbs up and subscribe to my channel.